All right, let's continue discussing planar graphs. So in the previous lecture, we talked about the properties of planar graphs, in particular with two connected planar graphs and three connected planar graphs. Now let's move on to the proof of Euler's formula. So most of you probably are familiar with Euler's formula. Which says the following, so that G be a connected graph, connected plane graph, and let V be the number of vertices, E be the number of edges, and F be the number of faces. Then V minus E plus F is constant. And what is this constant? I can look at the K1. So 1 minus, so 1 vertex minus 0 plus 1 face is 2. Right, if we look at K2, then it's 2 minus 1 plus 1 is 2. As the Euler's formula says that this number is invariant. And remember, why did I write plane instead of a planar? Because as we saw earlier, even if you have two isomorphic graphs, so if you're given a planar graph, there may be many different embedding on the plane, so faces are not uniquely determined. However, if you fix an embedding, then you can talk about faces. So this Euler's formula tells you that no matter which embedding you take, the number of faces will be still same. It's invariant, right? So remember, we had a what was the example? Yes, this is one example, right? These two graphs are isomorphic, so both are embeddings of the same graph, but they are not equivalent embeddings because you have a face with 5 edges incident. Here you have no face with 5 edges incident. However, the number of faces is same by this magic, right? So that's Euler's formula, and let's see how we prove it quickly. So it's going to be induction on number of edges, and it's trivial if you have no edges. That's K1, right? Actually, you can say more. It's trivial if G has no cycles. Why? Because in that case, G is a tree, and the number of vertices is number of edges minus 1, and number of faces is 1. Why do I say the number of faces is 1? If I have a tree embedded on the plane, now I need to prove that for any 2 points outside of a tree, any 2 points on the plane outside of the tree, I should be able to connect them by a curve, not crossing any points of the tree. So how do I know that I can cross? So I can do something like this. This can be done even if the tree is very complicated, right? So I might have a tree. I can draw the same tree in a weird way. So that's one edge, okay? And then I draw another edge. And then I draw one more edge. Okay, should I try? Okay, why not? And then I draw edge like this. Okay, this doesn't look like a tree, but it is a tree. And then you have 2 points on the plane. let's say here. Now, we need to prove that there is a curve connecting these two blue points because this is an embedding of a tree. And how do we do that? Well, well, you have to argue like this, right? So if I have a tree, I think of the choose a small epsilon so that I can think of the epsilon boundary of the tree, right? So I choose small ball around the tree. So radius is epsilon. And then I use this as my highway, right? So this is gonna be the idea. So for any 2 points, I can go to the red points and then follow this red line and then go to another blue point. The same here, right? I can go somewhere and then follow the path and then arrive here. Okay, so that's the idea. So f is 1. So now thus we may assume G has a cycle C, and let's choose an edge in the cycle and then apply induction on EC. On G delete E, and note that G delete E is connected. Because it was on the cycle. So even if I delete this edge, I still have a path connecting these two ends. Therefore, what we can do is apply induction to G delete E. So the number of vertices of G delete E minus number of edges of G delete E plus number of faces of G delete E is equal to 2. And by Jordan curve theorem, number of faces of G is one more than this. Why? Because both sides are distinct in G. Yeah. So what used to be distinct faces become one. What used to be one face in G delete E become two faces because it's bounded by a simple closed curve. So that allows you to apply induction. So the number of vertices of G is same. Number of edges of G is equal to number of edges of G delete E plus 1, right? So all of this tells you that number of vertices minus number of edges plus number of faces is 2. Is this best proof? Okay. There might be other proof, right? All right, so that's it. So that's Euler's formula, and by using Euler's formula, you can prove many things, and one of the most important consequences is the inequality on number of edges of the planar graph. So here's a proposition. If G is, so if I say graph is not simple, then number of edges could be infinite, a lot, right? Unbounded. But if graph is simple, then it's different. Simple planar graph with n vertices, then number of edges is 3n minus 6. unless, okay, if I stop here, then that's wrong statement, because when n is 1 or 2, that's counterexample. So, okay, right? Because when n is 1, 3m minus 6 is minus 3. When n is 2, right-hand side is 0, so there's no way that this is true. But other than that, this statement is true. So how do we prove that? And there are lots of places where the proof may break down, so we gotta be careful. All right, so I'm gonna apply induction. Probably. I mean, let me not say that. In order to prove this, so imagine, it's better to say induction. Induction on something. We choose this parameter later. Imagine that this statement is true for all smaller graphs, then I can assume that my graph G doesn't have any isolated vertex, right? So let me say we may assume G has no isolated vertex. So vertex is isolated if it has degree 0. We can assume the graph has no isolated vertex because otherwise I delete it, apply induction, and then add it back, right? So it increases n, but it doesn't increase number of edges. But actually, you can say more. G has no vertex of degree 1, right? If I have a vertex of degree 1, I can again win by induction because I delete this vertex of degree 1, go down by 1, and then apply induction. So you have inequality 3m minus 6 minus 1, right? So 3m minus 1 minus 6 plus 1. Why not? But actually, I should have said that this is true for small graphs, right? So we may assume again, n is at least, let's say, 4. Why not? If n is 3, then the graph may have at most 3 vertices, 3 edges, and 3 times 3 minus 6 is 3, so it's true. All right. Now, what else can I say? I can assume the graph is connected. Why? Because if not, I can partition graph into 2, G1 and G2. Now, I'm thinking that, okay, so if not, there is a partition. If not, okay, let's say G is the disjoint union of 2 graphs, G1 and G2. And I can assume that G1 is larger than G2. I mean, like let's say number of vertices of G1 is at least the number of vertices of G2, so we may but n is at least 4, so that means number of vertices of G1 is at least 2, right? So this has, okay, let's do it. I want it to be at least 3. How do I make it at least 3? So let's fix this to 5. Why? When n is 4, what happens if n is 4? So if I have 4 vertices, 4 choose 2 is 6. So that 6 is the maximum number of edges. Whereas 3 times 4 minus 6 is again 6. So this is tight. So I can assume that n is at least 5. That means G1 must have at least 3 vertices. That's good. Why do I care? Because I can then apply induction hypothesis. So EG1 is at least 3 times number of vertices of G1 minus 6. No, at most. Right. What about G2? I can say this. By the induction hypothesis. So I can say both of them. Why? Because if G2 has at least 3 vertices, then this is trivial inequality by the induction hypothesis. If G2 has 1 or 2 vertices only, then this is again true, because if you have a 1 vertex and 3 times 1 is bigger than 0. If 2 vertices, then 3 times 2 is 6, which is still bigger. So this is fine. I mean, it's not tight, but it's fine. Now add them together. So if you add them together, then you get what you wanted, right? So this is 3 minus 6. So therefore I can assume the graph is connected, otherwise we get it by induction. Alright. Now, by the same argument, we can assume the graph is too connected. Why? Because suppose not, then I have a vertex V and partition into 2 parts where there's no edge from left to right, right? So let me call this is my G1 and this is my G2. So I have edges like this. All right. And how many edges do I have in G1? All right. And since I know that there is no vertex of degree 1 or 0, so both of them has at least 2 vertices, right? If I have only 1 vertex here, then this vertex will have degree 1. But I already said that there's no vertex of degree 1. So that means both G1 and G2 have at least 3 vertices. That's good. Then we can apply induction hypothesis. EG1 is at most 3 times VG1 minus 6. EG2 is at most 3 times VG2 minus 6. And add them together, so EG is 3n plus 1, because 1 vertex is counted twice, minus 12. This is less than 3n minus 6. Okay, so we can assume the graph is too connected. Why did I say that? Because that makes it a lot easier, because now graph is too connected, so we can use this structure theorem saying that every phase boundary is a cycle of graphs. So every phase boundary is a cycle of graph G, and each edge is incident with exactly 2 faces of G, because graph is too connected. Now let's count number of pairs of an edge with face that are incident. Okay, how many pairs do we have? And it's equal to the number of edges times 2, because each edge is incident with exactly 2 faces. But if we count with respect to the faces, so this is the common technique in combinatorics. You count the same thing in two different ways, with respect to edges or with respect to faces. So for every face, you count the number of edges incident with it. But that's the number of edges in the boundary, and every cycle in the graph G contains at least 3 edges because the graph is simple. So this is 3 times f, where f is the number of faces. That's lower bound. So twice, let's write E as number of edges. Twice E is at least 3f. And let's write V as number of vertices. So V is equal to n. All right. So that means f is at most 2/3 of E. So V minus E plus f is 2 because the graph is connected. And f is at most something. So this is V minus E. Okay. Let's use n because I don't want to use different variables. So n minus E plus 2/3 E. So that means n plus 1/3 E is at least 2. So E is an minus. Yes. So E is at most 3 times n minus 2. Okay? So that's the proof. Here we use the fact that the two connected graphs have nice structure. And it's an easy exercise to follow the same proof and show that if G is bipartite, planar, simple bipartite planar, then number of edges is at most 2n minus 4. Why? Because it basically do the same thing, except here instead of 3 you have a 4. Okay, and then you get 4 here, and then you get 4 here, and then you get 4 here, and you get 1/2 here. So this will become 2. Right? So everything else is same. I didn't use anything about right. This proof I didn't add an edge. Sometimes I present a different proof. Instead of decomposing it by connected components or blocks, I might just add an edge. But in this proof I didn't do anything like that. So I think it's okay. All right. Now, why is this interesting? Because K5 has 10 edges and 5 vertices, and 3 times 5 minus 6 is 9. So that means K5 is non-planar. So we have seen many different reasons that why the K5 is non-planar. K33 still have the same thing. So 9 edges, 6 vertices, but twice 6 minus 4 is 8, which is bigger than 9. So K33 is non-planar. Right? Yes. Okay. Now we have seen many canonical reasons why these two graphs are not planar. And now we will talk about Kuratowski's theorem. Which states the following. Graph G, a graph G is planar if and only if G has no subgraph isomorphic to a subdivision of K5 or a subdivision of K33. In other words, let me say the other way. So in other words, G has no topological minor isomorphic to K5 or K33. So this is a characterization of planar graphs. So on the left hand side, when you say graph is planar, that means we have this embedding on the plane without edge crossings. I mean, having no edge crossings. Embedding already says that there's no crossings. However, on the right side, there's no geometry involved, nothing about geometry. It just says that you cannot find any subgraph isomorphic to a subdivision of K5 or subdivision of K33. So this property of some geometric property of graphs can be characterized completely combinatorially. That's the point of the Kuratowski's theorem. And now we have every tool we need to prove Kuratowski's theorem. Okay? So the proof will consist of two steps. First, we will prove it for three connected graphs, simple three connected graphs. And secondly, we use that to prove it for general graphs. So the step one, okay, let me just write step one to prove it for simple three connected graphs. Step two is prove the remaining. Why do we first focus on simple three connected graphs? Because then it's easier to deal with because of the structures. Now here's a nice concept of drawing an embedding of G is convex if every edge is a straight line segment. So I'm talking about the embedding on the plane. Every edge is a straight line segment. Every inner face is convex. So inner face means it's not outer face, so it's bounded face. Every inner face is convex. So convex means that whenever you pick 2 points, all the points on the straight line segment stays inside. So this is convex. This is not convex. Right? These 2 points, you go out. So it's not convex. And I will also talk about the convex, the infinite face, right? The complement of the outer face is convex. Then we say that embedding is convex. Okay? Now, so what graphs will have a convex embedding? I mean, it has to be planar, because I'm talking about planar embedding on the plane. And what else? If you have a parallel edges, you can never have a convex embedding because you're supposed to write the straight lines, right? So parallel edges we cannot have parallel edges. You cannot have loops because you can never draw a loop by straight lines. So it has to be simple. And if you have a cup vertex, then it's difficult to satisfy the condition about convexity because this face will never be convex, right? Yeah, no, complement of outer face is never convex. Or maybe you might have a situation where inside your graph you have a cup vertex, then this face is not convex, right? So you can see that in order to have a convex embedding, you need to have some connectivity. And actually, two connectivity is not enough, because I might have drawings like this, right? You have a face which is not convex. So even though, yeah, no matter how you try to draw this graph, you will end up with some face which is not convex. Right? So, okay, let me give you like a K23. Any drawing of K23. Oh, K23 is, we can make a K23, so K24, let's say. Any drawing of K24 will create some face which is not convex. All right, so, and the reason is graph is not reconnected. So here's a proposition, so which is a step towards the proving Kuratowski's theorem. Every simple reconnected graph with no topological minor isomorphic to K5 or K33 has a convex embedding in the plane. So I didn't say the graph is planar, but what I say is that any graph which is simply reconnected, has no topological minor, having no topological minor isomorphic to K5 or K33 will be planar. Not only it's planar, but it has convex embedding. It's very nice embedding. Right? And we proceed by induction on number of vertices. Perhaps. Well, let's do the number of edges. I think it doesn't matter. Oh. Okay, let's do number of vertices. Then it is trivial if number of vertices is at most 4, because if you have 4 vertices or less, then you never have any topological minor isomorphic to K5 or K33. Each of them has at least 5 vertices, and all of them has convex embedding. Oh, this is not reconnected. So the only reconnected graph on 4 vertices is K4. Because it's simple. And this is convex embedding. Now we use our theorem saying that in any reconnected graph with at least 5 vertices, there is an edge whose contractions make the reconnected graphs. Okay, do you remember? It's here, right? If you have a reconnected graph, then there is an edge such that you can contract it and make another reconnected graphs. So I'm going to use that. So yeah, so we may assume number of vertices is in list of 5, and there is an edge E, let's say the ends are xy, such that G contract E is reconnected. Okay. Now, I want to say something like this. The claim G contract E has no topological minor isomorphic to K5 or K33. Why? K33 is easier. Suppose I have a K33 topological minor, right? After contractions. This is actually quite easy to after contractions, you got K33. So does G have K33? Well, the vertex that you obtain by contracting could be somewhere. If it's outside of this subdivision, then you are done, because even if you uncontract, you still have a K33. If it's somewhere on the edge, let's say this was the edge that you create, and the vertex that you create by contracting E, then you might have two cases, right? So either this edge E was here, or it was like this, right, in G. So this is G contract E, so in G. So in both cases, you still have a path connecting these two vertices, right? What if you have a, oops, what if you have a vertex, this, as a contracted vertex? Now, in this case, you have three edges. Now, after uncontractions, when you end up with, maybe you have this, or you have that, right? But in both cases, you still have a subdivision. I can take this as my path, and in this case, it's the same. So in the case of K33, it's easy, right? So what I can say is G contract E has a topological minor isomorphic to K33 if and only if G has a topological minor. Oh, I don't have to say if and only if. Then G has isomorphic topological minor isomorphic to K33. But we assume that graph G has no K33 topological minor, so that's contradiction. How about K5? If I have a K5, it's easy. By the same argument, if the contracted vertex is here, then it's easy. Or here, it's easy. So the only place it may be non-trivial is this vertex. Now, there are two cases. There are maybe three cases. You might end up with, again, same, but the edge that you contract is here. Or maybe it's split into 1, 3, and edge E is here. In this case, it's easy, right? So this path is, again, this path. I'm going to take that as a path. But tricky case is when happens if you split like this. So that's the case we will worry. So G may look like this. And you have a subdivision like this. So in G. And in this case, what I do is to find the K33 topological minor. How? Well, let's say this is 1. So I'm gonna have a 1, 2, 3, A, B, C. And A, B, C is my choice. 1, 2, 3, A, B, C. And where do we choose two? Maybe let's choose here. So A, B, C. And 3, let's choose different color. A, B, I mean, looks same. Green, yeah. A, B, C. Right? So in this case, you have a K33 topological minor. So there's a conclusion. If G contract E has a topological minor isomorphic to K5, then G has a topological minor isomorphic to K33 or K5. Okay? But in both cases, we got a contradiction because we assume that such a thing doesn't exist. All right? So that's good. Why? Because I can apply induction hypothesis. Thus, G contract E has a convex embedding on the plane. All right. Now, let V be the vertex. Obtained from vertex of G contract E obtained from E. Since G contract E is 3 connected, G contract E delete V is 2 connected. So every base boundary of G contract E delete V is a cycle of G contract E delete V. So I will have a cycle. So there is a cycle C of G contract E delete V bounding the face of G contract E delete V containing V. So you have a cycle C which contains V in the embedding of in the convex embedding of G delete G not delete, it's contract E. All right. I can assume that this space is bounded, actually. Why? If you have convex embedding, you can choose your favorite face to be the outer face. How? Because you can draw the convex, you can do the stereographic projections. So you can draw the convex embedding on the sphere and rotate the sphere and then do the stereographic projection again. And that will give you another convex embedding. Of course, you have to change the edges, right? The edges will be different, but right, when you do the stereographic projections of the straight lines, it becomes straight line segments becomes part of the circle, right? Is it correct? Yeah, but anyway, you drew those convex embedding on the plane and rotate and then project it back, and then you can get another convex embedding, and that's how you get you can assume that face that you're interested, face that contains V is convex. Another way of proceeding this proof is probably say that you have a different proof for the case, particular case where this particular vertex is on an infinite face. I think both are fine. Yes, both are fine actually. In both cases, you can complete the proof. Maybe that's a better way of saying. So let's assume that the face of G contract E containing V is an inner face. So why? Because either you can say that, well, if you have a convex embedding, you will transform it to another convex embedding where this is a inner face. That's one way. Or maybe you can say that you do the same argument later by the similar argument. Even if this face is outer face, you can still do the same argument. And both sides are same, so let me proceed just one case. So here's a V. Now let's look at the neighbors of V. So x1, x2, x3, x4, x5, etc. xk. So let x1, x2, xk be the neighbors of V. Oh, did I cheat a little bit? Neighbors of V on C in the clockwise order. Where did I cheat? Okay, so I did cheat here. So sim of G contract E. So sim of G contract E is a simplification. So what I mean is I delete all parallel edges and loops. When you contract E, you may create the parallel edges. And if you do have parallel edges, then you cannot apply induction hypothesis. I'm gonna ignore all the parallel edges. So sim G contract E has a convex embedding then, right? Okay, so let me fix a little bit. So let H be this. Okay, now let's replace this by H. And H delete V is two connected. H delete V and H delete V. H delete V and here is H delete V. All right, so now we have this clockwise order. But V was obtained by contracting XY, so in G, it was like this. So neighbors of X and Y are these X1s to XK, right? So let's have more names so that PI be the path, subpath of C from Xi to Xi plus 1. So this is P1, P2, P4, and then this is PK. All right. Huh. Oh, okay. Maybe. All right. Let's change a little bit. So that instead of V, let's say this is X. Yes. Yeah, that will be better. And then there is a y. I want to draw y in a way, right? So x1, x2, x3, x4, x5, xk. These vertices are the neighbors of x on the cycle C in a cyclic order, and then the vertices of y have neighbors, some neighbors. So let y be the set of neighbors of y other than x. Okay? So in case 1, if y is in VPI for some I, if all neighbors of y are in some interval, then what is the case? You have a x here, and in some interval all the neighbors of y exist, then you can split like this. Then G has a convex embedding on the plane. Right? So I can assume that not all neighbors of y is in one interval. All right. Now what else do we have? If I have some vertex, some neighbor of y, all right, and this is in the pi, this is x, so and some vertex, if y has some neighbor outside of pi. Yeah. So if y has a neighbor two neighbors, let's say I used the a b, and such that this is, let's say, let's simplify, not simplify, but xi and xj, such if y has two neighbors a b, such that okay, let's say if x has two neighbors xi and xj, y has two neighbors a b, such that xi, xj, a b are distinct vertices on C, and the subpath from xi, no subpath from xi to x2 of C contains both A and B, right? So on one side you have A, on the other side you have B. Then G has topological minor, isomorphic to K33. Why? Because you are seeing it already, right? So this is, let's say 1, A, B, C, right? So 1 is adjacent to, okay, not C, this is C. 1 is adjacent to these 3, and whereas 2 is adjacent to A, B, C, so these 3, and what about 3? So C, oops, yeah. Oops. This C is adjacent, no, I should call it 3. 3 is adjacent to A, B, C. So you have a case 3. That's contradiction. So that means you can never have two neighbors y, which is in one of the internal vertex, and I mean by the first assumption, not all neighbors of y are in Pi. By the second assumption, if you have one internal neighbor, yeah. So by 1 and 2, y has no neighbor that is an interior vertex of Pi, right? Because Pi cannot contain all neighbors of y. But if you have if this is Pi, then if it has an other neighbor, then you already have a K33. So that means y is a subset of x1, x2, xk. All right? All right. That's by the way, why do I know that k is n is 2? If k is 1, okay, let's add some additional assumption. No, okay. Graph G was 3 connected, right? G is 3 connected, so both x and y have a degree at least 3. So that means k is n is 2 and y is n is 2. All right. Now, so every neighbor of y is one of the every neighbor of y is one of these vertex, right? Yes, if y is 2, oh, actually, yeah, I mean, we can use a symmetry. By symmetry, yes, okay, let me say that. So we may assume every neighbor of y other than x is a neighbor of x. By symmetry, we may assume every neighbor of x other than y is a neighbor of y. So that means y is equal to x1, x2, xk. Right? That's surprising. Now, if k is at least 3, so both x and y are adjacent to have at least 3 common neighbors, then you have a k5 topological minor. 1, 2, 3, 4, 5. G has a topological minor isomorphic to k5. So we may assume k is 2. But what does that mean? That means x and y have only 2 neighbors and they are common neighbors. What? Why is this possible? Then graph is not reconnected. Right? Because I can delete these 2 vertices and graph is disconnected. Alright, so that's the proof. Contradiction. Okay, so this shows that every simple 3-connected planar graph has a every simple 3-connected graph without K5 or K33 topological minor has a convex embedding on the plane. And in particular, every simple 3-connected planar graph has a convex embedding on the plane. So you can draw them on the plane without having made using only straight line segments, and all the inner faces are convex, or the outer faces are the complement of the outer faces are convex. What would you do if it's an outer face? If this is vertex that you are having, I mean, I didn't show how to do it for the other case when V is outside. Right? Again, you do the same argument, right? You can either try to find the locations of the last vertex y and see what happens. So I believe same argument works. All right, so that's the proof for the case when graph has good connectivity. In the next lecture, we will use this to deduce Kuratowski's theorem. Okay, that's it.